and I haven't talked about that yet. But yep.
Could you go over number 9, thermodynamics?
Sure.
Not the first one. Question.
Let's see. Homework. So, which one is it? Which set? Is it the first law?
The first law.
Okay. This one, the mass of. Okay. Yep. We just talked about that in office hours.
For a loop, for sure.
Okay. Yeah. You have to remember, I guess, a couple of physics equations or go get them. Okay, so you have a mass, and during this process, there's heat transfer. It tells you what that is, but then there's also a change in height and a change in speed. So in order to do this, you have to come up with the formulas that kinetic energy is equal to 1/2 mass speed squared. And that the gravitational potential energy is mgh. And so the change in kinetic energy is 1/2 mv final squared minus 1/2 mv initial squared. And the change in gravitational potential energy is mgh final minus mgh initial. Okay, so the first law says the change in the body's energy is equal to Q minus W. If I expand the meaning of delta E, that's the change in kinetic plus the change in potential, which is only gravitational in this case, plus the change in internal energy, and that's equal to Q minus W. W's are hard. Okay. Okay, so what do we know about this? So the mass, there's heat transfer at a rate of 5 kilojoules per kilogram. So the heat is equal to, I'm going to put everything in SI units. So kilojoules is 5,000 joules per kilogram. And then this thing has a mass of 10 kilograms. So this is 50,000 joules. There is no work done on the surroundings. So now we just have to deal with these changes in kinetic energy, potential energy, and internal energy. The change in kinetic energy, it goes from 15 meters per second to 30. So this is 1/2 times the mass times 30 squared minus 1/2 times the mass times 15 squared. And so I think that is 3375. Anyone else get that?
Yes. Yep.
Okay. The change in gravitational potential energy is mass times 9.81 times the final height. What does it say? The elevation decreases 50 meters. Okay, well, it doesn't give us what those heights are. You could make some up, or you could write. Notice that you can write this as mg times h final minus h initial. H final minus h initial is negative 50. Is that what it said? 50 meters? And so that is 500. So I think that is negative 4905. And the last one we have to deal with is the change in internal energy. We are given the change in specific internal energy. So the change in internal energy is equal to the mass times the change in specific internal energy. And that is 10 times a decrease of 5. So negative 50 joules. And we want to calculate W. So put this all in the equation. We have 3375 minus 4905 minus 50. That 50 is pathetic. Look how little it is. And then that's equal to 50,000 minus W. And so W is equal to.
Wait a minute, isn't it 5 kilojoules?
Yeah.
What?
It's specific.
10 times.
Oh, okay. Oh,
Not so pathetic after all.
I guess I'm sorry I made fun of it. 5 kilojoules. Dang it. Ooh, that changes everything. Okay, so W is equal to, let's see, we got 100,000 plus 4905.
Well, okay, so if it's losing temperature, would Q also be negative?
If it's losing,
Or
if it's losing heat, yeah, remember heat is energy.
right, but it's from the mass, so it'd be out of it, right?
Right, our system is the mass. Where does it talk about the heat?
At the top line.
Heat transfer from the mass. Yes, thank you. You are right. So this would be, so Q is negative 50,000. Okay. And so these just cancel each other. And so work is equal to whatever that is, 4905 minus 3375. So work is equal to 1530 joules. So does the system do work on the surroundings, or does the surroundings do work on the system?
Look, it's positive, so it does work.
It does work, right. So little by little, you need to internalize that sign convention, you know. Any other questions about that one?
No, it was the physics.
Yeah, right.
Well, I'm sorry to correct you again, but in the problem it states that the acceleration from gravity is 9.7.
What?
I saw
It
that.
really does?
What the hell?
What?
It's on like a really high airplane.
Yeah, seriously. Who wrote this problem? Okay, so this
So
is,
it actually is 4850 joules,
dang it.
not 4905.
Okay, 4850.
Well, they're getting caught up in your own curveballs.
Yeah. Actually, a lot of these in this class I got out of a book, so I might have just, so it's someone else's curveball, I think.
When I did it, I was just like, oh, he must have like really rounded.
Yeah.
Oh, yeah. Okay, so what do you get now?
1475.
Anything else anyone wants to complain about?
That W looks a little funny.
Yeah, right.
I can't really distinguish between the large U and the small U.
Yeah,
And again, the answer is yes, but not about this.
Yeah. Okay. But yeah, the main thing is, I mean, in this class, we're very rarely going to care about kinetic energy and potential energy. Sometimes it'll come up, but not very often. But you just have to remember those formulas from Physics 1, I guess. Any other homework questions you'd like to see before I... So I'm going to just keep going with heat transfer modes. And so the last one that we haven't done is convection. And in convection, heat is carried to a new location by moving particles. And the easiest way to think about this is like wind chill. So why is your exposed skin, why does it get colder faster if there's wind blowing? It's because if the air is perfectly still, your skin would warm up the surrounding air, and that would help insulate you, keep you warmer. But if that wind keeps blowing those warm particles away, and you keep having to warm up the air around you, you just get cold a lot faster. Has anyone here ever done a sport where you have to take ice baths? I don't recommend it at all. But so like if you're having like chronic inflammation or something, they fill a bathtub with ice and you say put your leg in there, and it's like if you're doing it and there's like a trainer watching you, you sit in there and it's horrible. And you're like, I just have to get through the first couple minutes. And you get through the first couple minutes and you're like, okay, I must be numb now because I don't notice it. But no, you're not numb. And then the trainer comes over. It's just that your leg is warming up the water. The trainer comes over and stirs the water, and then it feels just as bad again. And then you're still injured. It never works. It just makes you miserable.
Oh, weird level of fun.
Oh yeah, that's...
Don't do that.
Yeah, that's mean.
Yeah.
Okay, so for convection, Q dot is equal to a constant H times A times the temperature of the body minus the temperature of the fluid. So I'll write out what all these things mean. And remember that fluid can be a gas or a liquid. So like in the case of wind chill, I think people tend to think of fluid as meaning liquid, but we can also be talking about air. This H, this is like of the three modes of heat transfer, convection is the one that's farthest from being kind of like a law of nature. This is really just a curve fitting procedure more than anything. This H is like a catch-all that's measured experimentally for your particular case.
But it's sort of like kappa.
Yeah, kind of. Yeah. I mean,
And is that due to the randomness of a moving
Yeah.
matter?
that's right. I mean, it is sort of like kappa. That's actually a really nice way to think of it. It has to do with how fast the fluid's going, though, in addition to how readily the fluid takes up heat
So
from.
is it like a table for like fluid velocity and
There's no table that I'm aware of. You would just have to have your, if you know that you want to use this equation in a certain setting, you'd have to do some experiments to figure out what this H is in your case, and then you can use it for calculations. Yeah, this is the one that I don't think there's any way to just Google.
So for this age, you have to do the experiments first that you can predict, and you want to
Yeah.
make sure with the same stuff you're using.
Right, exactly. A is not the total. So remember with radiation, A was the surface area of the object. This is the surface area that's exposed to the fluid. So if half of the object is buried underground, you're only dealing with the surface area that the fluid is flowing over. So this is the surface area that's exposed to the fluid. TB is the temperature of the body. And TF is the temperature of the fluid.
Do we have to be in SI units in this?
No, you don't have to, but I always will be when I do these calculations. I mean, I just always convert to SI units before I do anything pretty much. So question, these temperatures if you're given the temperatures in Celsius, can you use that or do you have to convert to Kelvin?
you can use it?
You can use it because it's just a difference. And notice, you can't trust the signs from these heat equations when you're using them with the first law. That's true for this. Or radiation, or conduction. So in every case, when you see a heat problem where you're using the first law, just remind yourself right at the outset, after I do this calculation, I have to think about the direction that heat is moving. Okay? All right, so let's do a couple examples. So let's say we have a gearbox. So that's one gear. I'm not going to draw the teeth. And it's connected to another gear. Um, and there is work done here. I'll call that work 1. That's the input. And there is work 2 done here. This would be going the opposite direction, by the way. And that's the output. And the surface of the box is cooled by convection. Let's see. And we know that from our experiments, the constant of convection, H, is 0.171 kilowatts per meter squared Kelvin. Okay, so that's the units of H. This is a kilo, so I'm not falling for that again. The temperature of the surface of the box is 300 Kelvin. And the temperature of the air is 293 Kelvin. And the magnitude of the input work is 60 kilowatts. That kilo is trying to make me look stupid again, but I'm not falling for it.
You never look stupid.
Thank you. Thank you. I appreciate that. Okay, so here are the questions. What's the rate of heat transfer from convection? And then second, if this is steady state, what's the rate of work output? Okay, before I go into these, anyone remember what steady state means? What does that tell us for this problem? That term is going to come up pretty often on these.
Doesn't change.
The properties don't change, which means nothing on the left side of the first law, those rates of change are all 0. So E dot is 0. So kinetic energy dot is 0, potential energy dot is 0, and internal energy dot is 0. They don't change in time. Okay. Okay, so for the first one, we basically just have, I didn't give the, let's say that the area of the surface, this is a big box, 1 square meter of surface area. So for the first one, we're really just plugging it into the convection equation, and then let's think about the sign convention for the first law too. So we have that Q dot is equal to H. So I'm going to call that 0.171 times 10 to the third to put in SI units, times the surface area of the box, which was given as 1. And then since we're going to think about the direction of these, it doesn't really matter what order we think about. We're not worried about the signs yet. So let's say, okay, I'm going to do this as 300 minus 293. We don't care about the sign yet. So the order doesn't matter here. And so 0.171 times 10 to the third times 7, and you get 1197. And now we have to think about the sign of this as we're going to put it into the first law. So would this gearbox be gaining this energy or losing this energy? This, by the way, is in joules per second or watts. Remember, watts or joules per second. What?
Losing.
It is losing. Yep, it just has to do with which one has a higher temperature. And so...
Would you say that's because it's getting hot from the stuff that's happening inside of it?
That's right. Yep, there's friction or whatever going on inside. So the box is losing energy. And so for the first law, Q dot is negative 1197. So you have to think about that sign convention. Any questions about that? And now we'll go to the first law. Anytime you're using these heat transfer equations, the form of the first law you're going to use is the differential form. So we're going to use the form that says E dot is equal to Q dot minus W dot. This is 0 because it's steady state. And so we have 0 is equal to negative 1197. That's Q. And then minus, so what work do we have? There is work being done to the box that's equal to 60 kilowatts. Okay, so work done to the box, is that positive or negative W?
Negative.
Right, so here we have negative 60 times 10 to the third. And then the work that's being done by the gearbox on the surroundings, that's going to be a positive W2. So this is what we're trying to calculate. And so we have, let's see, 1197 is equal to 60 times 10 to the third minus W2. So W2 is equal to 58,803. And this should be W dot. Those dots need to stay there. And so this has units of watts. That means the rate at which work, in this case, is being done by the box.
It's like first derivative.
Yeah, that's right.
Specifically to
Yeah. Anytime you see a dot as a derivative in any class, it means a time derivative. It's a shorthand for, so this is defined as d dt. Okay, and that notation is going to come up a lot. And if you take dynamics, that's the notation you're going to see all the time.
I love in the sciences, there's all these little things that all of a sudden the teachers just start using.
Yeah, right. Yeah.
Because it's easier. Right? I mean,
Yeah, right. Except,
because you
and
wanna
it
find
is,
an easier
it's,
way to do
it's
it.
easier for everybody as long as someone tells you this. But if they assume your last teacher taught it to you, and like, it can be surprisingly confusing to all of a sudden see these dots, you know, so. I mean, I remember when I took like physics 2 in college, and just like right from the start, the teacher wrote ODEs, like solve this ODE, like ordinary differential equation. But I'd never heard of that before, so I just thought like an ode was some physics thing for like half the semester. That wasn't a great semester in many ways, but any other questions? Okay. Let's do another one. Okay, so I'm going to do one more example, and then that'll be it for today. And then we're going to get into some substance relationships, like pressure, volume, temperature type substance relationships next time. Okay, so let's say that there is a microchip that's embedded in some kind of material. And to cool it, there's a liquid flowing over. And the exposed area of the chip, the area of the chip that's exposed to the liquid, is 5 millimeters by 5 millimeters. And experimentally, it's been determined that the constant of convection is 150 watts per meter squared Kelvin.
And that's like specific to the silicone.
Yes, and specific to the speed of liquid flowing, and specific to that liquid. So yeah, that has to be determined pretty much in exactly this. But if you're doing a ton of these, you can do that experiment and then use that value in the rest of your calculations for all the rest of them, you know. But yeah, that's not something you really can't use other people's data on that unless it's a pretty identical situation. The electric power to the chip is 0.225 watts. This is a steady state process. And the temperature of the coolant is 20 degrees Celsius. What's the temperature of the surface of the chip?
I suppose this is actually like something you could potentially like be useful.
Yeah, right.
Like if you were measuring the two.
Yeah, for sure. Yep. I mean, I think both of these two cases are pretty, approaches that you would use in real situations. Okay, so well, let's start by figuring out the heat transfer, and then we'll go using the first law, and then we'll work backwards and calculate the temperature. Okay, so from the first law, we know that the EDT is equal to Q dot minus W dot. And electric power is always going to be represented by work. So let's figure out what that is. There is energy going into the chip from the electric power. So is that positive or negative W?
Negative.
That's right. W is positive when the system is doing work on the surroundings. The chip is our system. And so this is equal to Q dot minus negative 0.225. And this is steady state, so this is 0. And so Q dot is equal to negative 0.225 watts. Does it make sense if you have a case where your system is being cooled by convection that Q dot would be negative? Yes, that makes sense because a positive Q would be heat entering the system. This is heat leaving the system. And now we're going to...
And that's like a rate?
That's right, it's a rate. This is joules per second. Yep. And so now we're going to plug this, and we can forget about the negative sign now, but we're going to plug this into the convection equation. So negative 0.225, and now we can forget about this, is equal to RH times the exposed surface, the area of the exposed surface. So that is 5 times 10 to the minus third squared. And then times the difference in temperatures. So since we're just looking for the positive value here, we can put the higher temperature minus the lower temperature, So which temperature is higher, the fluid or the chip? Yeah, so we have the temperature of the chip minus 20. Since this is a difference in temperatures, we can just use Celsius. We don't have to convert to Kelvin. And so we have 0.225 is equal to 5 times 10 to the minus third squared. So that is 2.5 times 10 to the minus 5 times T minus 20. And so this thing times 20. And so we get 0.2255 is equal to 2.5 times 10 to the minus 5 T. And so the temperature is high. That is not right.
I got 80. I got 82.
What did I do here?
I got 9,020.
Be a hot chip.
Yeah.
9,000.
It would be a pile of. Oh, I just didn't multiply out the coefficient. I divided by the coefficient. Yeah, that's what I did.
It's operating on the sun.
Maybe I
Yeah, I got, hold on. This I don't think is multiplied by 150. That's the problem.
Oh,
2.5 times 10 to the minus 5 times 150. Okay, here we go. This I got the same thing as you, 9,000 degrees. Like, dang, that chip is doing a lot.
I want to know what it's made out of.
Yeah, it's very tough. Okay, so this should be 0.00375. If any of you guys, when you take Physics 2, one of the tables in the Physics 2 lab has a very distinct burn in the shape of a transistor. Those things, they get blazing hot if you do your calculations wrong and you're sending too much current through them. I don't know about 9,000 degrees though.
So I feel like it turned into like a plasma or something.
Yeah.
That's like almost, if it's Fahrenheit, that's almost the surface of the sun.
Yeah. 0.00375. Okay, now we're getting close. 0.00375 times 20 plus 0.225. So this is 0.3. And then divided by 0.00375. And it's a much more reasonable 80 degrees Celsius. Okay, any questions about that?
Can you just go again? I was gonna say with the gearbox, it was like easy for me to think about where the work was going.
Yeah.
In the case of the chip.
Yeah, well, we're just always going to call any kind of electric power coming in, that's going to be, negative
Work on the
W.
system.
And any electric power that's leaving, like later when we, like when we're talking about turbines and stuff, that can leave as mechanical work if it's just spinning some kind of shaft or something, or it can leave as electrical work if it's powering some kind of, generator or whatever. And in either case, just electricity leaving your system is going to be considered,
Doing work.
yeah, right. And electricity coming into the system is going to be considered work being done on the system.
So electric work is always going to be like external, it's not going to be like the change in internal energy.
Right, yes. If electricity is being generated and leaving the system, you're going to represent that as work.
Cool.
Okay, so
Thank you.
yeah.
In
Electricity-
the real world, is there generally like work happening both positive and negative at the same time?
Is there an overall thing for that?
Like because
Yeah.
like a hydro generator,
Mhm.
like if like the flow is inconsistent or whatever,
Yeah.
and they want to have like a consistent,
Mhm.
like they're pumping sometimes.
Yeah.
they're pumping,
I mean, I think that it's true that the more precisely you're trying to calculate it, I mean, there's always going to be some heat transfer. There's always going to be some work in or out due to volume changes. But
Yeah, because I suppose, like you said, like if it was turbulent, all of a sudden
Yeah.
the spinning rotor
Yeah,
or the turbine would hit that and
Right.
do work on it.
right. But we're going to do a lot of cases where we're trying to get a ballpark figure, and so we're going to leave out, smaller values of work being done or whatever. A lot of times we're going to leave out heat transfer because we're just going to say, well, it happens pretty fast. There's pretty good
Well,
insulation. That's going to be a small contribution. Any other questions? Okay, that's all. So yeah, look for an assignment, and we'll get into simple compressible substances next time.